Okay, so that's the second order cross partial. And so I've simply defined this quantity this way. You'd work that out if that quantity is positive and this is the second derivative with respect to x, if that's positive, then the function has a relative minimum at that point. Okay? If that quantity d is positive and the second partial derivative with respect to x is negative, then it has a relative maximum. Okay? If this quantity is negative, then this has neither a relative maximum nor a relative minimum at that point. It could be a saddle point. Okay? And if it's 0, then we actually don't know anything about those critical points. Okay? And this is sort of a pathological case where these quantities are exactly offsetting that quantity, which would be unusual. Okay. Okay, so that's everything on multivariate calculus. That is multivariate, certainly the differentiation side. We're going to jump into integration and summation in a second. But before I do that, how is everyone feeling comfortable? Okay, you're ready to jump into integration. Okay, so there are two fundamental calculus problems that people for millennia have been trying to solve and have succeeded in solving, of course, but with calculus. But the two fundamental problems are, one, to express the slope of a nonlinear function, okay, or find the slope of a curve at a particular point. So that's what we've been doing till now. The other related problem in calculus is to find the area under a curve. Okay, and it turns out that the problem of finding the area under a curve is actually related to the problem of finding the slope of a curve at a particular point. Okay? So finding the area of a region under a curve, how has it been done in the absence of calculus? Well, you could draw the curve, for example, this curve here. You could draw this curve and you could approximate the area under this curve, for example, simply by drawing a whole bunch of actually, the way a better approximation would be, excuse me, is to take a bunch of rectangles that approximate the area under that curve. You know how to compute the area of a rectangle. It's simply the length times the width. So you'd work out the area of each rectangle and then sum the areas over all those rectangles, right? So you could certainly do that, and that was the method by which the the definite and indefinite integrals were actually arrived at. Summing these areas is known as a Riemann sum. Okay, Riemann sum. Okay. And it turns out that the integral or the antiderivative is simply the limit of the sum of these rectangles as the width of each of these rectangles goes to 0. So of course if you reduced the width of these rectangles, you'd have many more rectangles to compute, many more smaller rectangles, and your approximation would get closer and closer to the actual area under the curve, because of course your errors are all here, where you're estimating too much here, too little here, and so on, right? So the narrower your rectangle, the more precise your approximation. And if the width of these rectangles go to 0, then the limit of the sum of these areas, the limit of the Riemann sum, will go to the integral. Okay, so keep in mind, when we talked about the derivative itself was a limit. There we were talking about a limit of the slope of a secant line as the distance, as some increment delta went to 0. Okay, so similarly the integral is derived through a limit. Okay, now so the derivative was a slope. It's the rate at which the function f is changing with respect to changes in the variable x, the rise over the run. Sometimes we know the rate of change, but we don't know the function itself. Okay? It turns out that when we do that, when we have that situation, we're really looking for the integral. For a moment, let's talk about the antiderivative. Think of the antiderivative not as the integral, but simply as what you get if you reverse the process of finding the derivative. Right? To find the derivative, you applied some rule. If you had a polynomial, you used the power function rule. So you had x squared, you took the derivative, you got 2x. Now, if you are faced with some function, I want you to reverse the rules of differentiation to get the antiderivative, the opposite of the derivative, right? So suppose fx is a given function, little fx, and capital Fx is a function that has little fx as its derivative. Okay, and you'll see this often. A capital letter will often denote the antiderivative function of the little letter. Okay, so capital F prime x is little fx. Okay, so we'll call capital F the integral or the antiderivative of little f. Okay, so this is, so far we're just talking in mechanical terms. Simply faced with a function, you simply reverse the rules that you use to get the derivative, and by applying those rules in reverse, you're getting an antiderivative. Okay. So what's the antiderivative of x squared? You can reverse the general power rule. If little fx is x squared, then the antiderivative is going to be, well, I've given you the answer there, but what's the logic you applied to get the derivative to, if you have some function x to the k, when you take a derivative, you get k x to the k minus 1. Okay, so you're taking this, putting that in front, and subtracting by 1. So to go back, well, you know that you're going to add 1 to the exponent. Okay, so if you had k minus 1, you're going to have k minus 1 plus 1. Okay? And what you did here was you multiplied by k, multiplied the term by k. So you're going to divide by, in this case, you're going to divide by the exponent. So you're going to divide by k minus 1. No, because here you're okay. So I'm starting out with this, right? Okay. So in that case, we had x squared. So suppose this is x squared. Then I'm just going to get, I'm going to end up with x to the 2. And that's k minus 1 plus 1. So I've got x cubed. And I've got to divide by, hold on. Yeah, I think you're right? It's got to be k plus 1 because I had here 2. That's right. Sorry, this should be k plus 1. So, because it has to be this and that. Because this is what I did when I went down here. Okay. So in this case, k plus 1 is 2 plus 1. So 1 over 1 divided by k plus 1, which is 3. Okay, so and you can always check if I have to take the derivative of this, well, that's going to be 3 over 3 times x squared, which is just x squared, which is what I had when I started out. Okay, so always do that check. Okay, now, but the slight complication is that, of course, when I take a derivative, if there happened to have been a constant in the original equation, if this was x to the k plus 2 or x to the k plus 6, I would still end up with kx to the k minus 1. So all of those would give me this derivative. So when I reverse and I go to the antiderivative, I have to keep in mind that whatever I get as an antiderivative plus some constant which I do not know. It could be because that it could have been any number that started out. Could have been a 5 or a 1. And we denote that the constant of integration, yes. Yeah, I'm just saying that if you start, suppose you started out with.
It's supposed to be also s to the power of k plus 1.
Sorry, x to the power of k plus 1.
The power of k plus 1.
Yeah, all I'm saying is that I start out with this, and then I add 1 to it. So that's why it's confusing, because it's not that I started out with k. You see? That's why we got confused before. I'm just trying to show you that I go back to the same place. So I'm saying I started out here with k minus 1. So this is what I had. I just added 1. Exactly. If it was k, this is what you have to do. This is the rule you have to apply. You just have to add 1. Okay? And that's what I'm doing there. I got x squared. I just added 1. But I have in mind that that x squared must have come from an x cubed.
It should be k minus 1 plus 1. Let's do that.
My k is, yeah, that's right. My k is,
K minus 1.
no. This is a different, this is a different k. Right? I still have, my k is going to be 3, and I'm definitely going to get 1 over 3. You see? So this is the beast. This is the exponent to which I add 1. Okay? And here I've got some coefficient. It so happens that those two things are related, but I'm just saying that what's the thing that I have to do to that to get back here? I'm going to divide by k plus 1.
But if you substitute, it doesn't add up.
This, you know, what the problem is that the notation is bad. This k is not the same as that k. This k is this k, right? So that's really, this is just a bad way of expressing the notation. Yes. So instead of x squared, let's suppose that we have 2x cubed. Okay? And that is the derivative. Okay? So now I know that that's the derivative, so I've got to go up 1. So f(x) has got to have a 4. Okay? Then I'm looking for the, I'm looking to divide. If I had a 4 here, I put the 4 there, but I ended up with a 2. Okay, so I've got to divide. Let's try that. If I do that, would that work? So that would be 2x cubed. Okay, but we just have to make sure if I put the 4 in front, I get a 2x cubed, and then plus c. Okay, so you just, I think instead of trying to apply that rule that I try to come up with on the fly, just ask yourself, put the exponent up by 1, put that exponent in front, and see what you'd have to divide by to get that. Okay, is that good, Sveta? Okay. Yeah, so I know, you know, one thing that I can be sure about is that the exponent is always going to go up by 1. So first do the exponent and ask yourself, well, if I had differentiated a term x to the 4, that 4 would have come in front, and it would have been something like 4x. But actually, I had 2x, so there must have been some coefficient that made the 4 go to 2. And what is that coefficient that I need to make that 4 go to 2?
But as a rule, could we not just take the new exponent?
Yeah, you could.
Divide by the new exponent.
Yeah, you could take this coefficient and divide by, yeah, which was the k plus 1 that I had before. So divide by, see, I put there k plus 1, that was the 3 plus 1, but it's a different k, that's why I don't want you to use that.
The rule should not, maybe the new exponent, you divide by the new exponent.
You divide by the new exponent. Forget the k, but divide by the new exponent, which is the old exponent plus 1. Yeah, if you have a polynomial function like this, okay, it won't be the case, for example, if you had x in the exponent. Remember, that's a different kind of function. We'll see that in a second. Okay, the C. Yeah, the C, right? Well, the reason for the C is that, okay, if I take a derivative of this function, then as you know, you get 2x cubed. Suppose that instead of this function, I had the following function, and I were to take a derivative of this, what would be the derivative? 2x cubed, right? Same as before. And similarly, if I had 300 there, right? So there are many, many different functions whose derivative is this. And they're all different from each other by some constant. And so that C is an indication of my ignorance. That is, I do not know the value of that constant. That could be a 0 or it could be some other number. Okay, so actually this is really a class of functions, all different from each other by a constant. Okay, so let's see. So this is, suppose you have to look for the antiderivative, 2x minus 1 over x squared. So this is a good, just to get some practice. Okay, so 2x minus, that's 1 over x squared. It's helpful to write it with the exponent. Okay, so that's minus x to the minus 2. Okay. And so what is f of x? Well, the 2x was what? Just x squared, right? So I raised the exponent by 1 and then divided this 2 by this 2, so I end up with a 1 here. And then here, I'm going to raise the exponent by 1. So that is minus 1. Okay, and then divide this coefficient by that. So this is minus 1 divided by minus 1, which is plus 1. Okay, plus the constant. Okay, and this, as you know, is just 1 over x. Okay, everybody feel comfortable? Okay, that is the indefinite integral, right? Little fx is a function whose antiderivative, actually I've written this as antiderivatives are big fx plus c, a whole class of functions. And how do I denote this? So this is just the notation. I'm sure you've seen this before, but just remind yourself. This is a script s for summation, because an integral is just a summation over a continuous interval of f of x dx. The dx denotes the tiny interval, the tiny widths of the imaginary rectangles that you can think of, which you use to construct the area under f of x. Okay, so the function inside this script s and dx is the derivative. Okay, that's what you have to find the antiderivative of, and that is the antiderivative. Okay. Okay. If this were dy, then it would be with respect to y, and so on. Okay, here's an example with, here's a useful example that you might come across. So suppose, so determine determine the antiderivative of x to the r, where r is a constant not equal to minus 1. So this is just a generalization of the problem we've been doing so far. Okay. So note that x to the r is the same as x to the r times r plus 1 over r plus 1. This is just equal to 1. So, okay, so it looks more obvious when you write it this way. X to the r is, of course, just x to the r over r plus 1 over r plus 1. Okay. So again, just using the power rule that we talked about before, this helps us to do the division of the coefficient that we did before. If I have to find, if x to the r is the derivative, the antiderivative is going to be x to the r plus 1. And then this has to, if I were taking a derivative, this would go in front, so it would be an r plus 1. But I have a 1 here, so what I have to do is to divide by r plus 1, right? So I'm going to get r plus 1, just as we did before. We take the new exponent and divide this by r plus 1. It may not help you to think about it this way. Well, you know, if you just want to think about it as take the new exponent and divide the old coefficient by the new exponent, that's fine. Okay, but here's why you want to know exactly why. Here's why you want to think about this. Because you're dividing by r plus 1, right? Well, what can you not divide by in our numerical imagination? By 0, right? So if r happens to be minus 1, then you can't carry out that division, which is why we're excluding the case that r is equal to minus 1. Okay, that was your question, right? Anybody know, for bonus credit, what the antiderivative is if r is minus 1? Yeah, it's the natural log, right? So that is, if r is minus 1, okay, that's the same as 1 over x. The antiderivative of 1 over x is the natural log of x, okay? And deriving that is beyond the scope of this evening's session. But just keep that in mind. It is actually something we use quite a lot in economics, the natural log and its derivative.